Hello students, today we are in lecture number 18 on classical electrodynamics. I was actually planning to give today's lecture on gauge transformation and in particular on Coulomb gauge. So that was the plan actually, original plan. But however, before giving an introduction to the gauge transformation, I would like to explain certain thing related to the yesterday's classwork. So because if we go back to the yesterday's classwork, let me therefore show it what we were doing in the last class. We were originally interested in calculating the curl of the magnetic field. That was the work, and we were evaluating using another vector quantity, what was known as the magnetic vector potential capital A. That was the work that we have done, and in fact we have completed it. But however, there is a point to be noted. The point is that while doing the evaluation of the curl of the magnetic field, we have seen that it can be written down into two integrals that are there. And in fact, the second integral was quite comfortable. So we were able to simplify this entire thing to mu naught into the current density. So mu naught into J. So that was comfortable. But the first integral, we have actually shown that it is equal to 0 in the last class. But however, the proof that or the reason that we have provided to say that this particular integral goes to 0 is not quantitative, or it is not a mathematical proof, but rather it is based on some kind of analogy to the electrical circuit, something like that. So we have seen that in the last class we have seen. So probably I'll just show what we have done so that you can remember. So we got this kind of a situation, and the argument for putting a 0 here is that this kind of expression is looking like. So you see the word like here. So this is not a mathematical proof, but we are providing some analogous situation where you make a comparison to kind of electrical circuit, wherein you can say that the algebraic sum of the current in a closed loop will be 0. And where from current comes is J dot ds is there. So J dot ds will provide a current, and because of the closed loop that goes to 0. So this is how we have provided some qualitative reason, and then we have made it 0, and then in fact we have completed the work in the last class. But the point that I would like to tell right now is that that was not a very solid mathematical proof. So okay. So for the purpose of understanding, or at least to say that this first integral goes to 0, to that extent, that particular expression or that analogy was nice. Okay, but however, for that purpose I would like to provide the explanation in today's class in a mathematical proof. That is, mathematically we can easily show, it's not very difficult. So I would like to show that without going into any analogous with electrical circuit, we can mathematically show that this particular integral I1 goes to 0. It is not difficult. We are going to use only the Gauss divergence theorem, but it takes only a few steps. So I would like to make this proof also, so that the previous lecture will be complete in terms of mathematical proof. So that is the plan. So the original plan is slightly diverted. The gauge transformation and the Coulomb gauge. So that will be discussed after completing this formal proof. So let us therefore proceed with this. So how we are going to write down this particular expression is that let us write down in the same way that we have done, namely the first step. So we will say that the integral will come first, and afterwards the differential operator will come. That is the idea that you have, and the rest of the thing is same. You simply copy that. The only thing is we already know that we have to keep some k and f. This we already seen. So we will maintain the same symbol for clarity. So you know what is k, and then you also know what is f. F is actually the current density. And once you have this, let us simply expand it. I mean, expand means what? The product rule. So you have the divergence of a product, right? So let us expand it as a two terms. UV rule, okay, product rule. So let me therefore write down the two terms. The first one is you will be having a scalar times the divergence of vector, then plus the vector dot the gradient of the scalar, and that's all. And you complete with whatever d omega is there, and then close the bracket. So it is a simple product rule that we are going to use. And once this is over, let us substitute whatever was the k and whatever was capital F. So that's what we are going to do. And integral is over omega prime, that was missing. So let us finish it. And then k is 1 by r. And capital F is capital J. J is a function of r prime, that you should remember. R prime. Okay. So J means r prime. And then of course k is once again that. And we are going to do a small manipulation with this. So let us therefore do the expression. The small manipulation that we are going to do is that we have to now remember which is a function of x, y, z, which is a function of x prime, y prime, z prime. Okay, so you always remember, right? Del operator is a function of x, y, z. Okay, that prime was missing, right? Okay, and j is a function of x prime, y prime, z prime. That is always there everywhere. And we are going to use this del to del prime. So we are going to convert to del prime. So therefore a minus will come. We have seen this. Of course, y minus will come. And then wherever the prime was missing, I think in the previous line. And once that is clear, we will understand that the term is going to 0. So whatever I am showing the green color, the reason, of course, you can easily understand why it goes to 0. Because the differential operator is a function of x, y, z. It is operating on something which is not at all related, which are primed variables. So because it is unrelated information, it is going to take the differentiation dou by dou x, dou by dou y. This term goes to 0. So we are left out with only this term. And here del, we are converting del to del prime. So that conversion gives you a minus sign. And this is actually coming from some other previous lecture which yesterday I showed, probably lecture number 11 or so. So you please verify that from the last class. I have given the lecture number and then the timestamp in the lecture where we have done the proof that shifting del to del prime will give you a minus there. So that proof we have done. So let us therefore put all the information here so that we will be having this expression. I1, this integral is given by, you have the j of r prime, then you have a prime was missing once again, and then the gradient prime of 1 by r. But there is a minus sign, so I put a minus sign here. So once that is clear, so now we have a fairly simple looking integral, but however we have to use once again the Gauss divergence theorem. Okay, so let us therefore use the Gauss divergence theorem so that we we will see how to simplify this. So I will write down, because we are moving to the pure mathematical expression. I will write the title. It is a rule coming from the vector calculus. So I will write in different color, so that after finishing the required mathematics, we will write in the white color. So as usual, you write down that the volume integral of the divergence of the vector function v will be equal to the closed surface integral of the vector function dot ds, means normal component. And that's all about it. And we are going to use v equal to k times f, as I explained in the last class. So let us substitute v equal to k times f. So let me finish that writing. Prime is not required now. Okay, this is purely mathematics, right? So no prime. So that's all. That is the Gauss divergence theorem. Now let us apply the product rule in the left side. So that means I am going to write down two terms. Two terms will come on the left hand side. So that is the first term, and the second term is plus, once again, integral. It is the f dot gradient of f. Sorry, f time gradient of a scalar. And then write down copy the right hand side. So basically we have used the product rule on the left hand side. That's why you have two terms. And let us now substitute k equal to 1 by r. Okay, we are going to substitute k equal to 1 by r. So I am writing in a different color. So probably I will explain what we are going to do. We are going to substitute, of course, k equal to 1 by r. But out of the three terms, there are three terms are there. This is 1, 2, 3. But out of the three terms, this is the term that we want, because this is how the equation looks like now. So therefore, we want the middle term. So I am going to write down the middle term here. So how much will be that? That is equal to the right hand side minus this. So this term you take it to the right hand side with a minus sign. Okay, so that is how we are going to write down, and afterwards we will substitute. So I'll write down that the gradient of the scalar, that will be equal to the right hand side of the expression f dot ds. Then you take the first term to the right hand side. So why we have done that is because this is how the equation looks like. So you just go back and verify, because you have written the first equation, right? You can verify, and we are going to substitute k equal to 1 by r, capital F equal to capital J. All these things we are going to substitute, and of course d omega will go, no, d omega also will go to d omega prime. So these are the changes that we are going to do. So let us therefore verify what was there in the previous expression, and then you can write down. So let me therefore finish this, then I will show what was there earlier. So now the integral becomes omega prime. Okay, now you see what are the substitutions, and accordingly you write down. Gradient becomes gradient prime. Okay, I think the prime I have not written. So gradient also goes to gradient prime. So I will write down that later. Then you have 1 by r j of r prime dot ds prime. So everything becomes a prime. Then you have a minus integral omega prime. K is 1 by r, then del prime. So I want to put a prime later. Okay, I'll finish this and put it d omega prime. So what is required, what is prime is missing is that del also should go to a prime. So that point I will write down now. Not only that, del operator should also go to del prime. So I will make all primes now. So that goes to prime. Similarly, another del also goes to prime. So this is the point that you have to note down. So for clarity, I will write down that this is the del prime operator. And of course, why do you want to use prime operator is we have seen in the equation number A. That's what we have done. So you verify the equation number A, then it will be clear for you. So I'll show that. So here you have, right, in this equation A, you have this del prime. So because equation A is already containing del prime, so we need everything in del prime operator, and J will be r prime d omega prime. So because of this reason, we are making the transition or equivalent replacement. That's all about it. Okay, see, the point that I am trying to explain is, in a pure mathematics textbook, you have d omega. Okay, that's the volume, that's all about it. But in physics, in our electrodynamics case, the volume is d omega prime. So which means that all d omega is actually d omega prime in our case. When you are transferring the mathematics equation to our application, this kind of equivalence has to be replaced. Okay, that's the point that I am trying to say. Similarly, f will be replaced by j of r prime, and usually if you don't require del prime, then you can maintain the original del. But just now we have already converted with the del prime with a minus sign here. So because of this reason, in this entire expression, the del should also correspond to the del prime operator. So that is what we are actually making. And here the point to be noted is that the important point to be noted is regarding the closed surface, what kind of surface that you are going to use. So this is quite a tricky point where many of the textbooks is not explaining, okay, what kind of surface that can be used in the Gauss divergence theorem. Okay, so this point is very important. So I will now explain that in the evaluation. So once this is clear, we are going to use the equation A now. Once again, remember, so what was there? Yeah, so there is one more point that I would like to explain. So here in the equation A, this is what we are going to copy. Now you have to be careful because there are two del operators are there. There is one here and there is one more here. So this one we are not at all using anywhere in our calculation. It is simply coming right from the beginning. Okay, that means from the yesterday's class. And we are only worrying about the integral here. This is the part of the integral that we are still doing. And this portion integral we are not at all touching. It is just staying there. And we are simply calling this expression as I1. So because this integral only we are planning to work out. So once this is over, we will try to evaluate the gradient. That's what is the plan. So therefore, what I'm trying to say is, when you are making a del prime here, this has no connection with that. That is what I'm trying to say. So we are performing something from here to here. So probably I will show a highlight. I will put some highlight here. So then you will be comfortable. So only that integral we are working. So the one which is previous to that, namely the mu 0 by 4 pi and then a gradient, this we are not at all touching. Okay, right from the beginning, from the yesterday's class. Okay, that is the reason. So this one you should not put a prime. That is what I am trying to explain now. Okay, once that is clear, let us now copy all these things here. And then let us open a bracket, and we are going to get two terms, right? So that is why. And the first term is a closed surface integral. And so I can write down this as j of r prime dot ds vector divided by script r. Then you have a minus integral. Now it is a volume integral. So I'll write omega prime. Then this is a del prime operator. Then you have j of r prime divided by script r d omega prime. That's all. So now you got two integrals. And let us see which is going to 0 now. So one of them goes to 0 very easily. And for that, you will have to recognize a continuity equation. Of course, in the last class, I explained what is continuity equation. The appearance of the continuity equation is like this. Divergence of the j is equal to negative of dou rho by dou t. That is the meaning. So here, I would like to explain here before writing. Divergence of j, when you write here without reference to a particular coordinate system, it means that the del and the j will be operating on the same coordinates. Okay, that is the meaning. If this is one coordinate and if that is another coordinate, then the differentiation is automatically 0. There is no need to keep this kind of expression at all. So that point should be clear. So are you able to grasp what I'm trying to say? If this is dou by dou x, dou by dou by dou by dou z, then this j is a function of x, y, z. Then only it can perform and then survive. Okay, that is the point. If this is x, y, z and that is x prime, y prime, z prime, then naturally this itself goes to 0. So why do you want to have this term and call this by the name continuity equation? So that option itself is not there. So the point is that the independent variables x, y, z is common for both of them. And if it is the case, now comes the point, and if it is the case, you see here, and you see here, this is del prime and that is also in the primed coordinate system. So therefore, I am going to write down that this is equivalent to del prime. That's an equivalent. Okay, it is equivalent to del prime. Then dot j is a function of r prime. These two are equivalent. So what are equivalent? Can you see? If I am changing del to del prime, j will be a function of primed variable. So both of them are primed variable now. In this case, both of them are an unprimed variable. That is the point that you have to capture now. And the rest of the thing is same. The remaining thing you simply write down dou rho by dou t equal to 0. And so now you understand by writing this, what is the purpose of writing the continuity equation is that we have this del prime dot j here. And remember, j is a function of primed variable. So such an object is there here. Therefore, what should be the value here is that value should be equal to the negative of the dou rho by dou t. That's what we are supposed to substitute here. But then now let us come to a particular special situation. We can always substitute this. Of course, dou rho by dou t can be substituted, but then this integral cannot go to 0. So this is going to be a little, okay, we have to think what to do. So now in order to avoid such a situation, you can ask the question, is there any chance that dou rho by dou t can go to 0? Is there any chance? The answer is yes. So dou rho by dou t will go to 0 if the charge density is not a function of time. And under that condition, this term can go to 0. Therefore, now you are asking the question that any chance is there for this going to 0? The answer is yes, provided the charge densities don't change with time. And that is exactly what we call the magnetostatic situation. That means when the charge distribution is not varying with respect to time, but the uniform charge density is moving with uniform speed, okay, then we will say that dou rho by dou t is 0. So therefore, the interesting point is now coming that only under some special situation it goes to 0. So let me write down whatever I explained now. All the things I explained, now I just show that these two terms are visible there. And coming to the last term now, so I will explain, or I will write down when this will go to 0. So for the case of the magnetostatics, we understand that rho, that means charge density, should not change with time. Okay, so what is the meaning? That means dou rho by dou t should be equal to 0. So if that term is 0, then what will happen? So already there is a 0. Remember, already there is a 0. If this term is also going to 0, then what is the meaning? The meaning is the del prime dot j is equal to 0. That's the meaning. And this is the expression that you have here. So ultimately what happens is, this is what is equal to 0. So this is equal to 0 if this term goes to 0. That is the meaning. So therefore I will now write down that this entire expression is going to 0 under the magnetostatics. So now you understand, or at least now we are happy that one of the terms are done to 0, and therefore we have left out with a single term which I am highlighting. So now we have only one integral. That is what I am trying to say. So this integral goes to 0. And remember that we have made this integral go to 0 purposefully under the magnetostatic condition. So if you want to say that no, I don't want to have a static condition, then remember that this particular term will not go to 0. And instead of that, you have to substitute negative of, so minus of the dou rho by dou t, you have to substitute here. That point you remember. And if it is the case, ultimately I1 will not go to 0. Okay, so that means for the dynamic situation, that means when you are talking about the electrodynamics, the first integral will not go to 0. That is a point to be noted. But however, let us make a special situation of the magnetostatics, and then the second term goes to 0. So now we are left out with only first term, and let us now see what can be done for the first term now. I'll write down the first term now. So simply copy that equation. I'm not doing anything, only write down the first term. Then you have the integral, etc. Closed integral, it's a surface integral, and j is a function of r prime, dot ds is also primed variable, and divided by script r. So here, this is the one which is coming from the Gauss divergence theorem. And therefore what happens is that now I will tell you what is the tricky point in the Gauss divergence theorem. So if you carefully search the Gauss divergence theorem and then understand what should be the surface, then this is what it is. The surface S is any surface that encloses the volume under consideration. So here the very important word that you have to capture is any surface. S is not well-defined single surface. Remember, S is not a single surface. You have the freedom to choose any surface as long as you enclose the volume under consideration. What is the meaning of volume under consideration? It is your physically conducting material, right? You have some kind of a thick wire or whatever it is, or it can be looking like a big stone material, conducting medium. So three-dimensional conducting medium, that is what is the volume that we are going to consider. And in that material, the current is flowing. Sorry, rho is not current, right? Current density, rho is charge density. So I have to put capital J there. Okay, so that is the current that is going to present. So here the point is, here the point should be clear now. The important point is the S that is coming under the closed surface in the integration is any surface, which means that you have the freedom to choose the surface as you like. That's the meaning. It is not a fixed surface and you don't have any freedom, not like that. So that is the point that you have to what you call grasp from the theorem of the Gauss. And what is the freedom? You have the freedom, but there is one condition. The condition is whatever be the surface that you choose inside that closed surface, the closed surface. Okay, the integral is a closed integral. Therefore, whatever surface that you are going to choose, inside that surface, your physical material should come. Whatever material is there, in that material anyway, electrical current is flowing. All that thing is fine. So. Inside that surface, everything should come. That means you have to now put a big enclosure and then close it, whether it is in the form of a spherical surface or a rectangular box, whatever, that doesn't matter. So the shape doesn't matter, size doesn't matter. Okay, so these things doesn't matter, but only thing is, of course, it has to be a smooth curve. Okay, discontinuity should not be there. That is the only requirement. So now that you are going to make use of this freedom to evaluate the integral in a much simple way. That is the whole story now. And in order to demonstrate what I am trying to say, I will first draw a diagram showing both the material and the big surface. So let me show that. Yeah, so this is the one. So if here, what is the meaning that I am trying to say is that you have some physical system here in which the current is flowing, and we are going to use the primed coordinates for all the current. In the entire volume you have the current, that is what we say current density. Okay, so the uniform current density is present in the physical system like this. Now what should be the surface for the integration? That is the question. First option is this. First option is the outer boundary. You have the outer boundary, right? So that is the boundary of the material. So the outermost boundary that is there on the physical material, that itself can serve for the integration. There is no problem. It is the outermost surface of the material itself. But however, if you choose like that, then evaluating the integral is not easy, and therefore we will make use of, or we will exploit the freedom of choosing a larger surface. So I am simply drawing a bigger sphere here in such a way that's what I'm trying to say. It's a large sphere. What is the purpose of the drawing the large sphere is that the sphere will enclose. Enclose means it will keep all the material under consideration inside. So it won't touch here. Okay, such that you can draw any large sphere as you like. So that is the freedom given by the Gauss divergence theorem, which we are making use of. And so what is the advantage of this? So what is the advantage is, the moment you say that this is the surface that I am going to consider, then there is something going to be special. And that's what I'm going to write down. If it is the case, then how much current will be flowing on the surface? So on this particular surface of the sphere, how much current will flow? No current will flow, right? Sorry, no current will flow. Because all the current is inside, right? Your physical material is well inside the sphere. And because of this reason, I will say that capital J vector is 0 on the surface of the sphere. Because it is a surface integral, right? Only on the surface you have to worry. So therefore, I am going to substitute capital J of R prime in the integration here. Yeah, so that is the integration where you have J. And I'm going to substitute a 0 here. And remember, because there's a S here. So this is the closed integral. So the surface is a closed surface. On that surface, J, I'm making 0. So because of this interesting reason, what happens is that the entire integral goes to 0. The entire integral goes to 0. So that is the interesting story here. So once this point is clear, now we can write down that I1 means this particular integral is equal to 0. And that is our conclusion. And therefore, what was the I1 that we started with? So let us go to the beginning. Even though this is the I1, let us go to the very beginning where we have written down the pink color expression, right? Yeah, that one. So this is the expression which is going to 0 ultimately. Okay, so it ultimately turns out that this particular integral, what is known as the surface integral, goes to 0. So this is a reasonably a formal mathematical proof, okay, where you don't have to make any kind of imagination with an electrical circuit. Okay, and that kind of explanation may not be satisfactory, but at least for a qualitative situation, the explanation that I have given in the last class, maybe for introductory purpose, that is okay. But I thought that you must have a proper mathematical proof that the integral 1 I1 goes to 0. But remember that, once again, you have to remember carefully that it is 0 only for magnetostatics. Okay, for dynamics it is not 0, some extra term will come. So that's all about it. And once the I1 is 0, you know what happened in the last class. That is the conclusion, that the curl of the magnetic field is equal to mu naught into J. So that is the conclusion. So therefore, probably in the next class I will discuss about the gauge transformation, and in particular the Coulomb gauge. Okay.